Hello, my name is Qinghan Xiao. I'm honored to present my paper entitled Cognitive Electronic Warfare, Conceptual Design and Architecture. First, I'd like to give my special thanks to the editors of International Journal of Artificial Intelligence and Expert Systems for awarding this paper the IGA 2020 Best Paper Award and giving me an opportunity to explain the paper in this video presentation. In the presentation, I used the framework of why, how, what to structure the discussion. Cognitive error is the third error of computing. It is about the use of computers to mimic human abilities, such as perceiving, thinking, learning, and decision making. To catch the cognitive wave, there have been growing research interests in the development of cognitive capabilities in various radio frequency technologies. Unlike the current EW system, which has separate electronic support system and electronic attack system, the cognitive EW system needs to integrate ES and EA missions. The major contribution of this paper lies in that a full system architecture is presented to address how the cognitive EW system should look like. Major features such as perception, learning, action loop, and feedback-based decision-making are described in detail. As mentioned above, the current EW system has several limitations, such as it relies on libraries of non-emitter waveforms and existing countermeasures. Therefore, cannot deal with previously unknown radar threat inserter. A possible solution is to make EW systems capable of intelligent behavior by mimicking human cognitive functions. When talking about cognitive EW systems, it is necessary to distinguish it from adaptive EW. Adaptive EW is reactive, that will adapt to a threat and respond with a pre-programmed solution. On the other hand, cognitive EW is proactive, that will operate as a dynamic closed-loop feedback system through the learning of threats, dynamic states, and the time-varying environmental conditions. The concept of cognitive EW is based on a perception learning action framework. The process cycle can be repeated as a loop between perception and action with the environment as external component. Here is a figure of the proposed architecture of cognitive EW system, with the key aspect of tight coupling between the cognitive ES and the cognitive EA subsystems. Following, I'd like to use a case study to show how the system works. First, the legacy processing module will be used to identify and locate previously known radar emitters. After all the previously known radar signals are taken out, if there doesn't exist any other radar signal, the leftover data should be just random noise. Otherwise, if there exists a previously unknown radar threat, although mixed with background noise, its pulses will show some signal pattern. Therefore, the leftover data will be processed by the cognitive ES module to characterize threat parameters. Based on the information passed by the cognitive ES subsystem, learning and reasoning are performed in EA subsystem to generate a jamming strategy. Summary. The objectives of this paper are twofold. First, functionally decompose the system into a meaningful integrated hierarchy in terms of its components and show the relationships among them. And second, identify directions for further research in the development of a prototype cognitive EW system. Because cognitive EW is a relatively new research area, there are not many articles on this subject. Most of the existing publications remain focused on introducing, explaining, and developing these concepts. The major contribution of this paper lies in establishing a full system architecture with both cognitive ES and cognitive EA subsystems described in detail. Before finishing my presentation, I'd like to express my thanks to the reviewers and editors for their careful review and valuable comments that have improved the quality of this paper. Thank you very much for your attention and interest in my paper.